start the recording to the cloud just now. Okay, please look up. Go ahead.
Okay, so thank you. Thank you for the introduction and for the invitation to this workshop. But yes, as the title says, I will discuss about small time asymptotics of first of the classical Schrödinger problem, which is a result obtained together with Giovanni Conforti, and also small time asymptotics for generalization of the classical Schrödinger problem to the metric setting, introduced and studied by myself together with Leonard Monsaint-Jean and Dmitry Vorotnikov. So for this reason, the talk will be divided essentially into parts. In the first one, I will introduce the classical Schrödinger problem. In this morning, Professor Mikami already introduced the classical Schrödinger problem and also its several different equivalent interpretations, in particular as a stochastic control problem. So I will just introduce those representations that are needed for sequel. And in this, from this preliminary description, it will be somehow clear that the Schrödinger problem can be seen as a noised, perturbed optimal transfer problem. So we'll review some results concerning this interest, the research carried out in this direction. So on the approximation of Wasserstein distance by means of the entropic cost, so the optimal value of the Schrödinger problem, and then state and prove the result obtained together with Giovanni Conforti. While in the second part, I will present the metric Schrödinger problem, so this generalization metric setting, discuss the setting, present some relevant examples that motivate the interest in this new problem, and then in the final, in the end, state and prove also the main results obtained together with Leonard and Dimitri. So let me start with the first part. So here I base myself on the seminal Schrödinger's thought experiments to assume that we have a number of independent and identically distributed particles, x1, xn, which evolve according to this diffusive SDE, and that are sampled at the initial time according to the invariant measure of SDE. And let me denote by mu Tn the empirical distribution at time t. Then, by Sanoff theorem, we know that the probability that the initial configuration is closed at certain probability mu is exponentially small as a function of the number of particles, and also as a function of the Boltzmann entropy of mu with respect to the invariant measure. And the same holds, of course, at the final time. So if we observe at the initial time a certain configuration close to mu, then by virtue of this SDE, we expect that the final configuration will be close to p epsilon mu, where p epsilon is the Markov semigroup, the diffusion semigroup associated to this SDE. But if instead, at the final time, we observe a configuration close to some probability nu different from p epsilon mu, then this means that something improbable, but still possible as the number of particles is finite, happened between the initial and the final observation. Whence the question addressed by Schrödinger, which reads as follows: conditionally on these two observations at the initial and final time, is it possible to reconstruct the most likely evolution between mu and nu? And in order to solve, to give an answer to this question, one has to look at the probability of the joint event. And again, by Sanoff-like arguments, it is possible to prove that this probability is again exponentially small, But this time, the function that determines the smallness of this probability is no longer the entropy, the Boltzmann entropy, with respect to the invariant measure, but is something more complicated, which I will denote by C epsilon and call entropic cost. And it is the optimal value of this variational problem, which is called the Schrödinger, nowadays called Schrödinger problem. So one has to, so this minimization problem reads as the minimization of the Boltzmann entropy on the path space among all probability measures with initial and final marginals mu and nu with respect to the law of our process X. And why solving this problem gives an answer to the Schrödinger question? Well, essentially because there is a unique minimizer to this problem, just by convexity, strict convexity of the Boltzmann entropy, and the marginal flow of this unique minimizer is the desired most likely evolution between mu and nu. This problem admits also a static formulation, and which is actually equivalent to the dynamical one, and this is just a matter of projection and disintegration, one, instead of looking at the path space, one can also look just at the couplings between mu and nu and minimize still the Boltzmann entropy, but with respect now to this, with respect to the joint law at the initial and final time of our process X. And this static formulation already allows us to understand why the Schrödinger problem is related to optimal transport. Since, for instance, if one takes as a process the Brownian one, so one consider Brownian particles in the Euclidean space, then R0 epsilon is nothing but this standard Gaussian. And plugging this expression into the definition of the static Schrödinger problem, one gets up to smaller order terms this expansion, which has been formalized by Mikami and subsequently by Mikami-Thiolin and Leonard in the most possible general framework of Polish spaces. And actually, the precise result is a gamma convergence result of the gamma convergence of the Schrödinger problem towards the quadratic optimal transport. And this in particular implies that the convergence of the optimal values, hence the convergence of the rescaled entropic cost towards the half squared Wasserstein distance between mu and nu. So after this has been obtained, a surge of interest has raised, also because of the several applications of Schrödinger problem in numerics, and therefore it is a natural question. It was a natural question to investigate also further order of approximation of the Wasserstein distance by means of the entropic cost. So the first order has been studied in a sequence of papers, first in the sense of gamma convergence, in the one-dimensional case by Adam, Pelletti, and Zimmer, and subsequently also by Renger, Erbar-Maas-Renger, and more recently in the pointwise sense by Pal, also for costs which are not necessarily the quadratic one, but let's say smooth perturbation of it. And at the first order, what appears is the sum of the entropy of the marginal constraints. At this point, myself, together with Giovanni Conforti, we improved this existing literature in a twofold way. First, on the one hand, we passed from the first to the second order. And on the one hand, we moved from results which hold true only in the Euclidean setting to a result which is instead valid on weighted Riemannian manifolds and actually also beyond on the so-called RCD spaces in the sense of Ambrosio, Gigi, and Savary. And what we proved is that in this framework, if there exists a Wasserstein geodesic between mu and nu with finite Fisher information, then the entropic cost, or the rescaled entropic cost, can be admits a Taylor expansion around epsilon equals 0 of this kind, where so the second order term, which appears now, is nothing but the Fisher information integrated in time of the Wasserstein geodesic between mu and nu. And the proof essentially goes as follows. The first main ingredient is a Benamou-Brenier-like formulation of the Schrödinger problem, again, which dates back to seminal papers by Mikami and later obtained by Angelo Pavone, Jean-Pierre Léonard, and Ripani in the Euclidean case for weighted measures. And eventually generalized by myself and Professor Gigi in the setting of RCD spaces, which tells us that the entropic cost, the Schrödinger problem, can be seen as a Benamou-Brenier formula perturbed by the Fisher information. And then the second main ingredient is the fact that the entropic cost is a regular function of the perturbation parameter epsilon, and its first derivative is linked in an elegant way to this quantity E, or minus E, which is the total energy of the system. And the fact that this quantity, which is constant in T, can be interpreted as an energy is quite intuitive, since this is nothing but the Hamiltonian associated to this Lagrangian evaluated along the unique critical curve. And the fact that this identity holds true essentially relies on the envelope theorem. So having this identity at hand, it is quite easy to, at least formally, to obtain the second order expansion that I mentioned before, since if one integrates this total derivative between 0 and epsilon, then by just by fundamental theorem of calculus, we get this first identity. And by algebraic manipulation, it is not difficult to see that the Fisher information along the unique minima, the Schrödinger bridge between mu and nu, is non-increasing as a function of epsilon. So this upper bound follows immediately, and is actually non-asymptotic in the sense that it holds for any epsilon positive. The lower bound instead is more tricky, since what one has to prove is, let's say, the technical part is to prove that the Fisher information is continuous at epsilon equals 0. And here we used some fine properties, fine convergence properties of the Schrödinger bridge towards the Wasserstein geodesic between mu and nu. And knowing that this that the Fisher information is continuous, then again the first step here, the inequality here, is again motivated by the monotonicity of the Fisher information. And then, thanks to this continuity property, it is possible to replace this Fisher information by the Fisher information of the Wasserstein geodesic plus smaller order terms. And this, I mean, coupling this, the upper bound with the lower one, gives us the desired second order Taylor expansion. But one has, at this point, let me pass to the second part of the talk. One could wonder if this result is actually specific of the Schrödinger problem, or is just a particular instance of a more general fact, of a more general theory. And this was the motivation that moved me, myself, and Léonard Monsangon and Dmitry Grotnikov. And the starting point is the following one. Again, let me recall you the Benamou-Brenier-like formulation of the Schrödinger problem. And we can see that this this variational problem is actually a particular case of a much more general variational problem, since this kinetic energy, since leveraging on the Otto calculus, so looking at the Wasserstein space endowed with Wasserstein distance as a sort of Riemannian manifold, one can recognize this kinetic energy to be nothing but the speed, the Wasserstein speed of this curve in P2. And on the other hand, the Fisher information here is nothing but the Wasserstein gradient, or the metric slope with respect to the Wasserstein distance of the Boltzmann entropy. So this means that this variational problem is a particular case of this much more general problem, which makes sense on any metric space. Here, gamma dot is the metric speed of the curve gamma. This is the slope of a given functional E. And as we shall see in a while, under reasonable assumptions on the metric space and on the functional E we consider, this variational problem shares many analogies with the classical Schrödinger problem. So just as a side remark, let me stress that this metric entropic cost is not exactly the entropic cost of the classical entropic cost. There is this factor epsilon, so there is a slight gap, which I will also recall in the following when it plays an important role. So let me now state the setting. So the assumption that we formulate on the metric space and on the functional E in order to make this problem here solvable and to obtain interesting results. So basic assumptions, which are quite standard, are the fact that XP is complete and separable. The functional E is lower semi-continuous and locally bounded from below. On the other hand, what is more demanding is the third and fourth hypothesis here. So the fact that the functional E generates an EVI lambda gradient flow for any point X in the space, and the existence of a sort of weak topology sigma on our space, so that every metric bounded set is sequentially sigma compact, and both the distance and the slope of E are sequentially lower to semi-continuous with respect to sigma. So just for those who are not maybe familiar with the metric theory of gradient flows, let me just say that in the inversion case, EVI flows are nothing but, all notions of gradient flows coincide, so the distinction is irrelevant. In the metric case, there are several ways to define a gradient flow. The EVI lambda is the strongest one, and essentially what we really need in the proof is the fact that EVI flows are lambda contractive. They are in particular EDE, so they are they are somehow the steepest curves of steepest descent, satisfying this condition. And moreover, they enjoy very nice regularization properties, in the sense that if gamma t is the evolution at time t of along the EVI flow, then this point enjoys an immediate regularization phenomenon, which makes it belongs to the domain of the metric slope. And moreover, we have a quantitative control both on E and on the slope of E at this point in terms of the initial point, of the distance from the initial point. Okay, after this digression, let me spend some more time on the on some examples that fall within this class, as just to convince you that this assumption, even if they might look demanding, in the end they're satisfied in many situations, and also this weak topology sigma in many concrete situations as a very natural candidate. So the first example is the mean field Schrödinger problem, recently introduced by Bakov, Comfort, Gentil, and Leonard. And the main motivation behind it is somehow the following. As I said at the beginning, in Schrödinger's thought experiment, all the particles were assumed to be independent, and with this underlying dynamics. And the independency condition is quite strong from a physical point of view. So for this reason, Bakov, Conforti, Gentil, and Leonard replaced the underlying dynamic written on the first line with this one, where interaction between particles is allowed. With these new dynamics, the empirical distributions still satisfy a large deviation principle. And in this case, the rate function is again a variational problem, which still involves the Boltzmann entropy, but there is a crucial difference. So, namely, the fact that the reference measure is no more fixed, but depends explicitly on the argument Q. More precisely, the reference measure, gamma Q, is the law of the unique strong solution of the McKean-Vlasov SDE, written here, which reflects the interaction between the particles. So, this problem falls within our metric Schrödinger problem, because if one assumes that the pairing potential W satisfies this bound, the upper one is technical. The lower bound instead is more geometric and crucial. Well, under this assumption, the mean field Schrödinger problem admits a Benamou-Brenier-like formulation of this kind. And if one develops this square, one can recognize that the terms appearing are a kinetic energy, square of the gradient of these two quantities here, which is nothing but the metric slope of this functional E, which is the sum of the Boltzmann entropy and a convolution term, while the double product, so the other term, gives a total derivative, which integrated between 0 and 1 gives just marginal terms depending on mu and nu. So we have a Benamou-Brenier. So this mean field Schrödinger problem reads exactly as the sum of kinetic squared kinetic, yes, as the sum of a kinetic energy plus and the slope of suitable functional squared. And for this functional E generates an EVI flow, which is ensured by the theory of Ambrosio, Gigi, and Savarin. And the natural candidate for the weak topology is nothing but the narrow topology. So all the assumptions are satisfied in this first example. A second one consists in a different choice of the a much more general choice of the penalizing function. In the classical Schrödinger problem, we have the kinetic energy is penalized by the gradient of the Boltzmann entropy, but one can also consider Wasserstein gradients of internal energies. So functional of this form, where U is a function satisfying the so-called McCann condition written here. In particular, Riemannian entropy falls within this class, just with this explicit choice of U. And also in this case, the existence of an EVI zero flow is granted. For instance, this is proved actually even in the metric measure setting by Ambrosio, Mondino, and Savarin. And again, the weak topology is the narrow topology on the Wasserstein space. A third and last example, which I think is quite relevant, is given by nonlinear mobilities. Since so far, we have seen how to penalize or regularize, depending on the point of view, the Wasserstein distance. But it is also possible to perform the same penalization technique, to apply the same penalization technique to distances other than the Wasserstein one. More precisely, one can consider the Dolbeault, the class of distances introduced by Dolbeault, Nazaré, and Savary, which are modeled by the Benamou-Bernier formula. But instead of the linear continuity equation, they are built on this nonlinear continuity equation, where the term m here, the so-called nonlinear mobility, appears also here in the kinetic energy that one wants to minimize. So it is possible to, in this case, to add the slope, an epsilon slope of arbitrary functional, actually of any internal energy described on in the previous slide. Again, the fact that these internal energies generate EVI flows is proved in this paper by Carrillo, Lisimi, Savary, and Slepch. And again, the weak topology is the narrow one. And I particularly like this third example also because it has very strong links with interacting particle systems, as for instance, simple exclusion processes and principal Landau models are linked to precisely to these nonlinear continuity equations. Even if I have to admit, together with Leonard Monsaint-Jean and Dmitry Vorotnikov, we had just a purely analytic and variational approach, so we didn't study this more probabilistic or stochastic interpretation of the problem. So after this motivational digression, let me now state the results we obtained. So the first one is just that the metric Schrödinger problem is meaningful, also in this setting. And the assumptions we formulate are nothing but the natural translation to the metric framework of the assumption that one has to impose also in the case of the classical Schrödinger problem. For the classical one, it is natural to ask that mu and nu have a finite entropy. Here we ask that x and y belong to the domain of E. And moreover, that there exists at least one curve connecting them, since we do not assume the space to be a length space or to be connected. Well, under this assumption, we have that the metric Schrödinger problem is solvable. And moreover, we have we proved as a sort of Moscow convergence result. More precisely, we have that the perturbed kinetic energy plus the indicator of the marginal constraints gamma converges as epsilon goes to 0 to the unperturbed kinetic energy, hence to the geodesic problem between x and y. And the gamma convergence takes place both with respect to the uniform in time metric convergence and the pointwise in time sigma convergence. So for this reason, this can be seen as a Moscow convergence result, since the gamma limit inequality holds true for the weaker notion, for the weaker convergence, which is the pointwise in time sigma convergence, while the recovery sequence built for the gamma lim sup inequality converges with respect to the uniform in time strong metric convergence. And moreover, since we have enough mild equicoercivity, we can also prove that optimal values converges optimal values, and up to subsequences minimizers converges to minimizers, which is let's say not surprising, but still is quite useful also for what comes next. And how do we prove this result? Well, both the well-posedness of the problem and the gamma-lim sup inequality. The gamma-lim inf one is straightforward. It's just lower semi-continuous kinetic and slope. Well, the gamma-lim sup and well-posedness both follow more or less the same line, and which is inspired by a paper by Tamanini and Savary. And essentially, our strategy is the following. Essentially, given any curve gamma, which is here represented below in the picture, we regularize it by applying the EVI gradient flow along it. So moving here in the picture in the vertical direction, and thus obtaining a curve gamma tilde, which is the diagonal here, which has a very nice property compared to the original one. And it is actually possible to control both the speed and the slope of E along gamma tilde just in terms of the speed of gamma. And how can we do it? Well, essentially, we argue by triangle inequality. We first move in the horizontal direction. And here we use the fact that along this horizontal curve, we have run the EVI semigroup for the same amount of time. So in particular, we can use lambda contractivity, the semigroup, while here in the vertical direction, we are moving along the EVI flow itself. So we have even better regularizing properties. And combining this, we can prove well-posedness, actually well-posedness for any choice of the regularization parameter function h here. While if we choose h as this h epsilon, then we get also the desired recovery sequence. More precisely, filling the details into this sketched proof, what we are actually able to prove is this inequality. So for we are able to control the distance between any 2 points along gamma tilde. Or let me just say here, t plus and t minus are just fancy notations for they are either t1 or t0 depending on the value of h at that time. So if h t0 is greater than h t1, then one has t plus is t1. Otherwise, if it is the other way around, then it's just t0. But I mean, it's not so important. What is interesting to stress here is that on the left-hand side, we have the distance squared between any 2 points along gamma tilde. We have the squared slope of E along gamma tilde times this term that in the end it will become first derivative of h squared. And we also have this term, which is the total derivative of E along gamma tilde. And all these 3 terms are controlled just in terms of the speed of gamma. So, and this is the desired regularization property we wanted, since we are just requiring that gamma is absolutely continuous. So we only know that this quantity is finite, but this allows to deduce that also the left-hand side, when integrated between 0 and 1, is finite as well. And as you can see, so if h, this holds actually for any h. And just to show that A epsilon is controlled along this regularization, and this allows to deduce the well-posedness, since then just by standard arguments in calculus of variation, this grants enough compactness. While if H is precisely the one written here, then the extra term appearing on the right-hand side vanish as epsilon goes to 0. And so in the end, this shows that gamma epsilon is precisely a recovery sequence. And this proves actually the gamma convergence, the Moscow convergence theorem. As a byproduct of this result, together with Mont-Saint-Jean and Bohotnikov, we extended the result presented at the beginning of the talk obtained with Conforti. So the second order expansion of the entropic cost. In this setting, again, the assumption we formulate are the natural translation of the one we had in the previous theorem. In that case, we had the unique Wasserstein geodesic between mu and nu had to have finite Fisher information integrated in time. Here we assume that there exists at least one length minimizing curve with finite, let me call it metric Fisher, integrated in time Fisher information. Then under this assumption, we have that the cost is regular enough, and the metric entropic cost admits a second order Taylor expansion around epsilon equals 0, which is again of the same form we had at the beginning. For the classical Schrödinger problem, we had epsilon squared times the integrated in time Fisher information of the Wasserstein geodesic. Here we have the infimum due to, since we're not assuming that since there might be more than one length minimizing curve between x and y, so we minimize the metric Fisher information among all these length minimizing curves. And moreover, an additional property that was not present in the case of the classical Schrödinger problem, since in that case the Wasserstein geodesic between mu and nu was unique, is that since by gamma convergence we know that minimizers converge to minimizer, we know that up to subsequences, omega, if we take minimizers for the epsilon Schrödinger problem, we know that up to subsequences, this omega epsilon converge to a minimizer of the geodesic problem. The fact is that this minimizer, omega star, is always Fisher information minimizing among all solutions of the geodesic problem. And to prove this theorem, the strategy again follows closely the one for the classical Schrödinger problem. The first step is again to investigate the regularity of the entropic cost. Again, due to the lack of uniqueness of the solution, the derivative of the metric entropic cost is not so nice. One has to distinguish between left and right derivatives, but again, almost everywhere they coincide, and this one can recognize these formulas as the metric generalization to the metric realm of what we had in the case of the classical Schrödinger problem. Again, one can see this analogy taking into account this slight gap in the notation. And so with this gap in mind, one can see that the formula on the last line here, that is what we had in the classical Schrödinger problem, is precisely what we have here, up to this maximization or minimization of over all possible epsilon Schrödinger bridges. Well, this identity allows us to, again, by fundamental theorem of calculus, to obtain this identity. And again, the Fisher information satisfies a sort of monotonicity property, which allows to obtain a non-asymptotic upper bound, which holds true for any positive epsilon, while again is the lower bound, which is quite more tricky. But again, here we use the gamma convergence of the Schrödinger, of the metric Schrödinger problem, which was not actually available in the classic. We has not been proved for the classical Schrödinger problem, and that's why, in that case, we relied on refined convergence property obtained in a previous paper by G. Well, here, leveraging on this result, we are able to circumvent the lack of this refined convergence property. And still, we are able to deduce that the Fisher information, actually the infimum over the set of minimizers of the epsilon Schrödinger problem of the Fisher information is continuous as a function of epsilon, also at epsilon equals 0. And therefore, we are able to replace this term here with this one up to smaller order terms. And again, combining this, the upper bound and the lower one, we deduce the desired second order expansion as stated before. And this concludes also the time I have, I think. And anyway, it concludes my presentation. So I thank you for your attention.
Thank you very much, Luca, for this night talk. Any questions either online or in the audience, as usual? Oh, let me just get the microphone to Christian Leonard. Sorry? Oh, yeah. Well, yeah. All right. Yeah.
Hi, Luca. It's Christian. Well, I have two technical questions. The one, but why Moscow convergence versus usual gamma convergence? And the second one is your function capital C of x and y as a function of epsilon. Mm-hmm. In your last hypothesis should have a vanishing derivative as epsilon tends to 0. Mm-hmm. So, well, I understand that this means that there is a smooth behavior of yes. The way that if you put some noise, this doesn't destroy too much. Mm-hmm. And are there all the examples that you have presented satisfy this hypothesis?
No, wait. So the fact that the derivative, that the function is right differentiable at epsilon equals 0 is not an hypothesis. Is part of what we prove.
Oh, sure. Okay. All right. Thank you. So this answers my question.
Okay. Fact, this explains. This was somehow just to explain why we don't have first order term, but we just have second order term. But anyway, this was somehow quite clear since the original problem has an epsilon squared, so it's quite intuitive that one has to just second order term and not.
All right. Okay. So thank you. Yeah, very good answer to my question. Thank you. And what about Moscow? What about Moscow versus gamma convergence?
Okay, maybe it's just an abuse of notation. It's just that I say Moscow convergence since the gamma limit inequality holds with respect to this convergence, which is the weaker of the two. And while the recovery sequence, so given any gamma, we are able to build a sequence gamma epsilon which converges to gamma not just in this weak topology, but in the strong one.
Stronger topology. Okay.
So, I mean, it's quite an abuse of notation since Moscow convergence usually is weak and weak start topology. I mean, is in a Hilbert setting, but still.
All right.
So since we have these two these two natural topologies, one is stronger, one is weaker. I just say the entre guillemets Moscow convergence.
Okay. Yes. Thank you. Another question, Luca.
Yep.
Yeah. Okay. I have a general question. That in the classical optimal transport theory, mm-hmm. they are able to construct an analog of Riemannian structure on the probabilities yes. on the space of probabilities, right?
Yeah.
And they can also figure out the tangent space of that Riemannian structure, right?
Mm-hmm. Yes.
And so my question is, can we do the similar things by the relative entropy?
No, so, what do you mean?
I mean,
I'm missing the question. So you mean,
does the relative entropy provide some metric structure on the space of probabilities?
well, I mean, I think that information geometry is sensitive. I mean, entropy is a divergence, and also by means of the entropic cost, it is also possible to build other divergences, which allows to interpret to say to describe in a geometric way the space of probability measures. But I don't know if it is possible to perform a pseudo-Riemannian theory with this with just the entropy. I mean, as far as I know, usually one needs a distance to build objects like. I mean, I'm more familiar with the Otto theory, so with.
Okay.
But maybe, I mean, I know that there are these. I mean, in general, also with divergences, it's possible to.
Okay.
To describe it as geometric way P2. So probably yes, but I don't know if notions like tangent and like that are available.
Okay, thank you.
Okay, so